Okay, so let's get started. So today we're going to do a short lecture where we're going to finish the material of Chapter 4 with a couple of examples of using this new method that we're going to introduce called the Ruthian. And then after that, I didn't have much planned for today. I don't want to start a new chapter before the midterm, so I'll remain available for the rest of the lecture if you have questions related to assignment 4 or the material in general in preparation for the midterm. Next Tuesday, however, we will do a tutorial session specifically aimed at the midterm, and so I'll do a few examples that are representative of what you may find on the midterm. Okay. So let me start with a summary of what we saw on Tuesday. We identified several useful properties of the Lagrangian. And so let me summarize the more useful ones here. So we found that if the Lagrangian does not depend explicitly on time, that is, di L by di T equals to 0, so there are no T terms inside of the Lagrangian. Careful, that's different than saying dl by dt, right? dl by dt is not 0 because L depends on the coordinates, and the coordinates themselves depend on time. However, the partial derivative of the Lagrangian may be 0. So if the Lagrangian does not depend explicitly on time, the Jacobi integral h, lowercase h, is a constant. So lowercase h, the Jacobi integral, is defined to be, first, there's a sum over the degrees of freedom of qi dot multiplied by di L by di qi dot. So you do this sum, and then you subtract the Lagrangian. So you can always define this, but if the Lagrangian does not depend explicitly on time, then h is a constant. So saying that mathematically, if di L by di T equals 0, then dh by dt equals to 0. Right? And so if d by dt, the total derivative of something with respect to time, is equal to 0, that thing is constant in time. So furthermore, if the potential energy that goes into the Lagrangian is not a function of the velocities, so what I mean is the potential energy is a function only of the coordinates, not their time derivatives. And that's generally true, right? The potential energy usually depends on position, not velocity, except in the annoying case of electromagnetism. So it's generally true that the potential energy does not depend on velocities. So if that's true, and if the kinetic energy can be written as a sum over J of K and a sum over J and K of AJK QJ dot QK dot. So if T can be written this way, so T is linear, is quadratic in the velocity, and that's true in general as well. So it's not such a limiting assumption. So if those two things are true, and only in that case, then H turns out to be equal to T plus V, and we know that that is the total energy. So essentially, if the Lagrangian doesn't depend on time, this quantity H is conserved. Furthermore, if the potential doesn't depend on the velocities and the kinetic energy is quadratic in the velocities, then H is actually the total energy. And so this is a generalized version of conservation of energy. So we may find that there's a conserved quantity H that's not total energy because the last two conditions aren't satisfied. So it's more general than just conservation of energy. Okay? And this quantity H is related to what we call the Hamiltonian. And we'll see in the second part of the course, we'll switch from working with the Lagrangian L to a more powerful object called the Hamiltonian H, and that connects to quantum mechanics. Although it turns out the Hamiltonian is very good for understanding quantum mechanics, but once you go back to quantum field theory, which is a more modern version of quantum mechanics, then they use the Lagrangian again. Okay? Any questions about that? So we also introduce cyclic coordinates. And they're going to form the topic of discussion for today. We say that a coordinate is cyclic if the Lagrangian does not depend explicitly on that coordinate. So the coordinate QJ is cyclic if di-L by di-QJ equals to 0. So again, you should be getting a flavor of this, or familiar with the, every time we say something doesn't depend explicitly on something, literally we mean that the partial derivative of that thing with respect to something is 0. That's what it means to not depend explicitly. So that's the definition of cyclic. So why are cyclic coordinates particularly useful and a desirable thing to have? Well, recall that the Euler-Lagrange equation is satisfied for each coordinate. So for each coordinate, we must have d by dt of di-L by di-QJ dot minus di-L by di-QJ equals to 0. That's the Euler-Lagrange equation. That's true for all j. Now, if Qj is cyclic, then the second term in the Euler-Lagrange equation is 0, by definition. So what does that mean? That means that we only have one term, and that's d by dt of dial by diqj dot equals to 0. And as usual, we like when the total time derivative of something is 0, because that means something is constant. So that means that dial by diqj dot is equal to a constant. And that's a useful equation, because dial by diqj dot is going to be typically only involve qj dots. It's not going to involve any double dots. Whereas d by dt of dial by diqj dot is going to involve double dots. Second order derivatives with respect to time. So if we can get rid of that d by dt, then we have a first order differential equation, and that's much easier to solve. So it's very desirable. Okay? So we saw that last time, and now let's start with the next section on what we call the generalized momentum. So we have generalized coordinates, generalized velocities, generalized forces, so might as well have generalized momentum as well, right? So generalized momentum. So remember, the theme here is that we add the word generalized in front of a quantity we're familiar with, and then that quantity is a more general version. So a coordinate might not necessarily have units of distance. A generalized force might not have dimensions of force. It may have dimensions of torque. So similarly, a generalized momentum, just based on our assumptions about English, generalized momentum we may find or may not expect to have necessarily units of momentum or dimensions of momentum. Okay. So what is generalized momentum? So we define Pi to be dial by diqi dot. So first of all, the generalized momentum is not defined until you know what the Lagrangian is. So you have to write out the Lagrangian to be able to figure out what the generalized momentum is. We say that Pi is the conjugate momentum to the coordinate Qi. So that kind of makes sense, right? We have a set of Qi's, and for each one of them, we can define this generalized momentum. Right? There's a Pi for each Qi, and the way you find it is you do dial by diqi dot. But there's a one-to-one correspondence between the momenta, the generalized momenta, and the coordinates. There are as many generalized momenta as there are coordinates. And so a neat thing that you might notice now, the definition of the generalized momentum is dial by diqi dot. But we just saw above that for a cyclic coordinate, dial by diqi dot is a constant. So for a cyclic coordinate, pi is equal to a constant. So the generalized momentum, conservation of it, automatically comes out of a coordinate being cyclic. So let me again write down the Euler-Lagrange equation. So we have d by dt of di-L by di-Qi dot minus di-L by di-Qi equals to 0. Well, let me just put in the momentum there. So di-L by di-Qi is pi, right? And if I move this to the other side, I have d by dt of pi is di-L by di-Qi. Now that should look actually kind of familiar, right? You have a name for that equation. And the name of that equation is Newton's second law. Alright, so let me just do an aside. F equals ma. That's the same as F equals dp by dt, right? You've all seen that, right? Because P is mv, so if you do d by dt of mv, you get m times dv by dt, and dv by dt is a. And then F is equal to minus di-v by di-q for a conservative force. So remember here, we're only doing conservative forces, right? We can ignore annoying things like friction. So all forces are conservative, so all forces come from a potential. And so L is equal to T minus V. T hardly ever depends on Q. It typically only depends on the Q dot. It typically only depends on the, no, I'm sorry. T hardly ever depends on the Q's, only on the Q dots, especially in Cartesian coordinates. And so a very specific case then is that since L equals T minus V, the T part, d by dq of T is usually 0, so di-L by di-Q is typically minus di-V by di-Q. And so that's typically the force that you get from the potential. Okay, so the Euler-Lagrange equation, if we write it as such, you can see it's Newton's second law is just a special case of it. Which makes sense, right? It needs to be consistent with Newton's second law. So let's do an example. Well, I guess I'll just use a new page. This is example 4.9 from the notes. And so what is the generalized, or what are the generalized momenta for a free particle in spherical coordinates? No, polar coordinates, sorry. it's a free particle, so there's no forces, right? So the Lagrangian for a free particle is the kinetic energy. V is equal to 0. And so you know how to find the kinetic energy in polar coordinates. The kinetic energy is 1/2 times m, and then the velocity is r dot squared plus r squared theta dot squared plus z dot squared. So here's an example of where t actually depends on one of the coordinates. But a special case of Newton's law doesn't actually fit here. It does in Cartesian coordinates, but here the kinetic energy actually depends on the coordinate r. So we have 3 coordinates, right? R, theta, and z. So we should be able to define conjugate momenta for each of those 3 coordinates. So the conjugate momenta of those 3 coordinates, the generalized momenta, well, the first one is PR, and that's defined to be di-L by di-R dot. Right? The definition of the generalized momentum, di-L by di-Q I dot. Right? So let's do di-L by di-R dot. Well, there's only one R dot term in there. That's the 1/2 mr dot squared. So if I differentiate, I get mr dot. I do the same thing for theta. So p theta is defined to be di-L by di-theta dot. If I do di-L by di-theta dot, I only have one term with theta dot in it. That's 1/2 mr squared theta dot squared. If I differentiate, it brings down the 2 and cancels the 1/2. And I get mr squared theta dot. And if I do PV, it's di-L by di-Z dot, and that's just going to be mZ dot. So if we look at our Lagrangians, what coordinates are cyclic? Coordinates are cyclic if they don't appear explicitly in the Lagrangian. So Z is cyclic because there are no Z's in this Lagrangian. Similarly, theta is cyclic because there's no thetas. There's a theta dot, but there's no thetas. Whereas R, there's an R. There's an R squared multiplying the theta dot squared. So that's not cyclic. So now, from the properties of cyclic coordinates, we see that p theta and pz are conserved. PR is not conserved. Well, let's look at p theta and pz. So what pz maybe is obvious, right? Pz is the momentum in the z direction because we use polar coordinates, so the z direction is unchanged from Cartesian. So it's a free particle, so we certainly expect the momentum, in fact we expect the linear momentum in all 3 directions to be conserved. So here we see that at least the momentum in the z direction is conserved because the z coordinate is cyclic. Now the p theta quantity is also conserved, but it's clearly not the linear momentum. Can anybody tell what that is? P theta? So looking at the notes? So Pz is easy. It's the linear momentum. And Z. Well, P theta is the angular momentum. Right? So simply by writing the Lagrangian for a free particle and using polar coordinates, conservation of angular momentum is sort of landed on our laps. That's pretty neat. And so we wrote out the Lagrangian in polar coordinates, and we found that there are 3 quantities that are conserved. Okay, so what if we had done it instead in Cartesian coordinates? So in Cartesian coordinates, the Lagrangian for a free particle is a half m, and then we have x dot squared, y dot squared, plus z dot squared. So here we have 3 coordinates, so 3 generalized momenta. So px is mx dot, and then we won't be too surprised if py is my dot, and pz is mz dot. So x, y, and z are all cyclic. Hence, px, py, and pz are all conserved. That's kind of strange. We do the problem in polar coordinates, and we only have 2 things that are conserved. But we do it in Cartesian coordinates, and we have 3 things that are conserved. So I'll let you ponder that. But it's interesting how the conservation of momenta, or angular momenta, just falls out onto your lap, and it depends on which coordinates you've chosen for the problem. So a hint of what's to come is, wouldn't it be nice if all the coordinates were cyclic? Because if all the coordinates are cyclic, then all the conjugate momenta are conserved, and it's very easy to write out the equations of motion for the system. And so at the end of the course, we will arrive to a method that allows us to find the correct set of coordinates where all of them are cyclic. And so that'll make the equations of motion very easy to solve. The caveat, of course, is that finding that set of coordinates is now the difficult problem. So we can shift the problem of solving the equations of motion, solving the physics of the system. Instead of doing that, we can solve a different problem, which is finding the correct coordinate transformations that give us all cyclic coordinates. That's like changing a problem of physics to a problem of geometry. It's a very powerful notion. Okay. Any questions about that? So now I want to introduce the Ruthian. It was developed by somebody called Ruth. So it's not so interesting in itself, the Ruthian. However, the method that we use to do this new way of the Lagrangian using the Ruthian is useful because it's a simplified version of what we'll do next when we do the Hamiltonian and we try to find out an expression that makes all the coordinates cyclic. Right? Our holy grail here is to have a description of physics that all the coordinates are cyclic, and it's just immediately solved. And then you just have to ask your mathematician's friends to find the correct coordinate transformations for you. So this method of the Ruthian has some of the features that are involved in those later derivations, and so it's helpful in that sense that we go through it now. So the idea between the Ruthians is that you have this Lagrangian, and some of the coordinates are cyclic. So those coordinates are easy to deal with because the conjugate momenta are constants, and that allows us to solve for the coordinates usually pretty easily. So can't we instead arrive at a description that has less coordinates to begin with, so that we don't need to even deal with these cyclic coordinates? And that's the method developed by Routh. So suppose the Lagrangian L has n degrees of freedom and the first k coordinates are cyclic. So the first k coordinates are cyclic. That means that di-L by di-Qi dot, that's the conjugate momenta of that cyclic coordinate, are constant. And we're going to call those constants beta I. So that's true for I equals 1 to k. I think I can make my beta look prettier. More on. I'll have to practice making betas. So I choose to call it beta I instead of pi to distinguish the fact that it's constant. So we'll call it beta I instead of pi to highlight that it's constant. So only for the first k variables is this true. Okay? So it's only for I equals 1 to k that the di-L by di-Qi dot are constants that we call beta I. So we can write L in terms of beta I for the I less than k, and eliminate the Qi dot for I less than or equal to k. So you have the Lagrangian. You take di-L by di-Qi dot, which is going to depend on Qi dot, and set that equal to beta I. So then you can express Qi dot in terms of beta I. So you can express Qi dot in terms of constants. And then you can substitute that back into the Lagrangian, and now the Lagrangian doesn't have any Qi dots where I is smaller than k. Okay? We then build the Roothian. So we define the Roothian R to be L. Now L is written in terms of the beta I's minus the sum from I equals 1 to k of beta I Qi dot. So it's only for the first k terms that we do this sum, and that gives us the Roothian. So the Ruthian is a function of, this is an awkward way to write it, it's a function of qi dot, beta I, and t. We have to be careful because the indices on the qi and qi dot set I bigger than k, whereas the i's that are on the betas are i's less than or equal to k. So a little bit awkward way of writing it. Maybe I should use different indices, but it's still awkward if I use different indices. Like j and I instead. So I don't know. Maybe you guys can suggest a better way to write it out. Okay, so far there's nothing I'm not allowed to do, right? Maybe it's not obvious why I would do any of these things, but they're all reasonable things to do. So, allowed, anyway. Maybe they're not reasonable. So it's important that I understand what the Ruthian depends on. Because what I'm going to do next is I'm going to take the variation of the Ruthian with respect to the things that it depends on. That's our favorite thing, the chain rule. So consider the variation of the Ruthian. So we want delta of R, and I'll just write out explicitly that R depends on qi dot, beta I, and t. Okay? So if I do the variation of something with respect to the things, so I want to know how delta R changes when I change delta Q, delta qi dot, delta beta I, and delta t. Except delta t, t is the independent coordinate, right? So there's no delta t's in it. I apply the chain rule, right? So I have to do how does R depend on qi, how does R depend on qi dot, etc. So if I apply the chain rule, I'm going to have terms with delta qi's, delta qi dots, delta beta i's. So let's start with the delta qi terms. So for the QIs, I goes to k plus 1, from k plus 1 to n. Right? The Ruthian, we've removed, well, there's no cyclic coordinates, right? So they're not in there anyway. For the QIs less than k, there aren't any in the Lagrangian, so there aren't going to be any in the Ruthian as well, because they're cyclic. So we only have the QIs that are bigger than k. So the chain rule term that comes from them is di-r by di-qi delta qi. And we have a similar term from the qi dots. That's from I equals k plus 1 to n of di-r by di-qi dot delta qi dot. Then we have the beta i's. So that's a sum. Now, for the beta i's, I goes from 1 to k. Di-r by di beta I delta beta I. And then we have to always add in this term at the end, di-r by di t. There's no delta t because there's no variation with respect to time, but there's still the partial derivative. Right, so if this is confusing to you, you need to go back to the first lecture of the course where we went through how to take the chain rule on the variation. This is very much the same thing as when we do delta Q and Q depends on other coordinates. So that's one way that I can write delta R. Now I can also write delta of, remember how R is defined? R is defined as L minus the sum from I equals 1 to K of beta I QI dot. Remember? we introduced the root in and we said it was equal to L minus that sum. Just the definition. Let me take the variation of that. That's also equal to delta R, right? Well, first we have to do the variation of L. So again, L depends on Qi and Qi dots and T. Now, L, because the Qi's are cyclic, or some of them are, the sum over the Qi, again, only starts at I equals K plus 1, and it goes to N. And I have di L by di Qi, delta Qi. Then I have a term, same thing, for the velocities. So I equals K plus 1 to N di L by di Qi dot delta Qi dot. Then I have the usual partial time derivative. And then I have minus delta of the sum from I equals 1 to K of beta I Qi dot. So if I write this out, the first three terms are the same. I have the sum from I equals 1 to N of di L by di Qi delta Qi. Sorry, that's I equals K plus 1 to N. Then I have the second term is the same again. I equals K plus 1 to N di L by di Qi dot delta Qi dot plus di L by dt. And then minus, now you take the variation of the sum. So the variation of the sum is the sum of the variations. That's back to the first lecture, properties of the delta operator. Just typically they're very similar to the differential operator. So the derivative of a sum is the sum of the derivative. So the variation of a sum is the sum of the variations. All right, so I can bring the delta inside, and it's the delta of beta I Qi dot. And so that's the product rule, just like you would do for a derivative. If you're taking the derivative of beta I Qi dot, you would do the derivative of beta I times Qi dot, and then you do the derivative of Qi dot times beta I. So if I do that, then I have the sum from I equals 1 to K. So the first term would be beta I delta Qi dot. And then the second term would be Qi dot delta beta I. Okay? So if I write this out, the first three terms are the same again. I equals K plus 1 to N, di L by di Qi delta Qi, plus the sum from I equals K plus 1 to N of di L by di Qi dot delta Qi dot, plus di L by di T. Then I have minus the sum from I equals 1 to K. Now what I'm going to do is I'm going to write the beta I, remember, is the same as di L by di Qi dot. Delta Qi. Or that's the definition of beta I, was di L by di Qi dot. And then the second term, it's just the same. It's, well, let me write it out separately. as a second sum here, minus the sum from I equals 1 to k. And then the other term, I'm not going to change it, so it's just qi dot delta beta I. Now, what did we do? First, we had the Lagrangian. And then for each cyclic coordinate, we did dial by diqi dot equals beta I, so we created a constant. Then we rewrote the Lagrangian, and we got rid of the qi dots that corresponds to beta I. So we removed the first k qi dots from the Lagrangian. Right? I said here, we can write L in terms of beta I and eliminate the qi dots for the I smaller than k. So L doesn't have any qi dots where I is smaller than k. I look at the second last term here. I have the sum from I equals 1 to k of diL by diqi dot. So I just said L doesn't have any of the qi dots where I is smaller than k. Inside of L, I'm doing diL by diqi dot, and I've explicitly written diL L to remove those qi dots. So that second to last term is 0. Because L does not have qi dots with I less than k in it. So finally, we write it again, just without the last term in it. So we have the sum from I equals 1 to, for I equals k plus 1 to n of diL by diqi delta qi plus the sum from I equals k plus 1 to n of diL by diqi dot delta qi dot plus diL by dt, and then the last term minus the sum from I equals 1 to k of qi dot delta beta I. So remember, that's equal to delta R. That's the delta R that I get when I write R as L minus the sum. If I just consider the fact that R depends, what variables that does R depend on, then I can also write delta R as the first equation on this page. So these two things are equal, obviously, because they're the same thing. They're both delta R. And they each tell us how delta R, or how R changes when I change the things that R depends on. Qi, qi dot, beta I, and t. So writing it the first way or the second way, I should expect the same amount of change if I change delta qi. It really shouldn't depend on how I chose to write it out. Well, that means I can identify the terms and set them equal to each other between the two expressions. Well, by that I mean that consider the first term in the first way of writing delta R. The first term is the sum from k plus 1 to n of something times delta qi. Well, that's the same thing down here. It's a sum from k plus 1 to n of something times delta qi. So that thing must be the same. So in the second equation, that thing is diL by diqi. In the first equation, that thing is dir by diqi. So by equating the two expressions for delta R and matching terms in delta qi dot, and delta beta I, we find that, so the first thing I said was that dir by diqi equals di-L by di-Qi. So we have di-R by di-Qi equals di-L by di-Qi. Second term is the terms in delta Qi dot. So I have a di-R by di-Qi dot, and then down here I have a di-L by di-Qi dot. So we have a second equation that di-R by di-Qi dot is equal to di-L by di-Qi dot. What else? I have a di-L by di-T term, and I have a di-R by di-T term, so they're equal as well. Di-R by di-T is equal to di-L by di-T. And then the fourth relation that I have is by matching the terms in delta beta I. So here I have di-R by di-beta I. Oops, too far. And down here I have minus Qi dot delta beta I. So I have oops. I said di-R by di-beta I equals minus Qi dot. All right? That's only true, well, most of them are only true for I equals 1 to k, or for I equals k plus 1 to n. So this one here explicitly, of course, because the betas only go from 1 to k, that one is true for I equals 1 to k. Okay, so now we've identified these four relationships between this completely randomly defined Ruthian, or maybe not completely randomly, but so far not very well justified. We have these relations between the Ruthian and the Lagrangian. So how are they useful? So because di-R by di-Qi is the same as di-L by di-Qi, and di-R by di-Qi dot is the same as di-L by di-Qi dot, then R must also follow the Euler-Lagrange equation, right? So let me just label these four equations in red. Call that 1, 2, 3, 4. So because of equation 1 and equation 2, R must also follow the Euler-Lagrange equation. So that means that d by dt of di-R by di-Qi dot minus di-R by di-Qi, because those things are literally equal to the L versions, so they're interchangeable, that must be equal to 0. Now it's only, of course, useful for I equals k plus 1 to n. Right? Because R doesn't have any of the Qi dots for I less than k. And then similarly, we can use equation 4 and just rewrite it out. I have, so Qi dot, that's the same thing as dqi by dt, that's just what it means. That's equal to minus dir by diqi. And that's for I equals 1 to k. So have we really succeeded in what we're trying to do? We're trying to arrive at a new description that does not involve the cyclic coordinates. So we want to get rid of the cyclic coordinates and we want something that's very easy to solve. So we write the Lagrangian so that the cyclic coordinates are the ones that we label with the first k indices. For those cyclic coordinates, we can easily solve the equations of motion by applying the equation I've labeled as equation B. So equations of once you have this Ruthian, the equations of motion for the cyclic coordinates is trivial because it's just qi dot equals dir is minus dir by, sorry, that should be a beta I, not a qi. Minus dir by di beta I. And then for the coordinates that are not cyclic, then we just have to solve the Euler-Lagrange equation. So we have succeeded in what we're trying to do. We're trying to make it easier to deal with a non-cyclic coordinate. So we completely get rid of them, and then we can simply write out that their time derivatives are equal to some derivative of the Ruthian. And then the coordinates that aren't cyclic, well, tough luck. We still have to handle them the same way, so they still follow the Euler-Lagrange equation with the Ruthian instead of the Lagrangian. But of course, they still follow. You could have L in there instead of R because dir by diqi dot is the same as dl by diqi dot. We showed that. So the strategy here, and I wrote out the steps in the notes of how you solve the problem, and I'll just do an example problem so that you can see it in action. I won't write out the strategy, except to say that for cyclic coordinates, the equations of motion are given by B, which is much more simple. And then for non-cyclic coordinates, the equations of motion are given by A, which is the Euler-Lagrange equation. That's the same as they were before. So let's do an example of this. Example 410. They're a little bit obscure to solve, but you can write a procedure that allows you to solve all of these problems in a way, and that's the procedure that I wrote in the notes, and we're just going to apply it here. So let's use the Ruthian on a particle subject to gravity. So I just mean our usual problem. So let's do it in Cartesian coordinates, and let's have a Lagrangian that's given by t minus v in Cartesian coordinates. So half m x dot squared plus y dot squared plus z dot squared minus gravitational potential energy, and we'll use the z-axis pointing upwards, so it's minus mgv. Okay? By now, if you're not able to just write out a Lagrangian for a simple situation like this, you should practice it. There are many examples online. All right. So the first step here is to identify the cyclic coordinates. So step one cyclic coordinates. Coordinates that don't appear explicitly in the Lagrangian. Coordinates for which dial by that coordinate are 0. Well, x and y are both cyclic. Z is not because it appears in potential energy. So x and y are cyclic. So we must now calculate beta x and beta y. Those are the things that are conserved for the corresponding cyclic coordinates. So beta x is equal to dial by x dot. Remember, betas are just the value of the conjugate momentum. The conjugate momentum is conserved, and it's conserved and stays equal to the value beta. That's the way to think about it. So beta x is easy to write. In fact, we already did it earlier in the lecture when we were talking about momentum. So dial by x dot is just mx dot. Same thing, beta y, dial by y dot, that's my dot. Now we have to eliminate x dot and y dot from the Lagrangian. Remember, that was one of the key steps that allowed us to say, many pages ago, that's one of the key steps that allowed us to drop that term when we're doing this derivation. We said, well, we've managed to write the Lagrangian in a way that it doesn't depend on the velocities associated with the cyclic coordinates. So we need to remove, in our Lagrangian, the x dot and y dot, and we need to replace them in favor of our betas. So that's not too hard, because look at our equations for beta x and beta y. Easy for me to say that x dot is equal to beta x over m. And similarly, y dot is beta y over m. So I can substitute that into the Lagrangian. The Lagrangian is half m, half m times x dot squared, well, x dot squared is beta x squared over m squared, y dot squared is beta y squared over m squared, and of course the z dot squared stays because it's not cyclic, minus mgz. Alright, now we have the Lagrangian, and we'll remove the velocities associated with the cyclic coordinates. So now we have the Lagrangian in the form that we want. Now we can write out the Roothian. What was the Roothian? The Roothian was R, is defined to be L. What was it defined to be? It was L minus the sum of beta I qi dot. So it's L minus the sum of beta I qi dot. Okay. So that's equal to L. So let me just write L. So I have a half m. And I have a beta x squared over m squared. I have a beta y squared over m squared. And I have a z dot squared, and I have a minus mgz, and now minus this sum. So the sum of beta I qi dot, so this I is going to take two values, right? I is going to be x or y. So the first one, let's say it's x, so that's beta x times x dot, plus beta y times y dot. Okay, so that's the Ruthian. But the Ruthian has x dots and y dots in it, so we don't want x dots and y dots, we want to get rid of them. We just put them back in. But that's okay, because we know how to get rid of them anyway. We know how to express them in terms of betas. So we have to do that again. So I'll write the first part again. So half m beta x squared over m squared plus beta y squared over m squared plus z dot squared minus mgz minus, so x dot is beta x over m, right? So I have minus beta x squared over m minus beta y squared over m. Right, it's beta x times beta x over m, beta x squared over m. Beta y times beta y over m, which is beta y squared over m. Well, in the first term, I have a half beta x squared over m, right? Because the half m in the kinetic energy term cancels one of the m's in the denominators of the two terms that have betas in them. So I have 1 over 2m beta x squared plus beta y squared minus beta x squared over m minus beta y squared over m. So if I group them all together, let me first write out the non-cyclic coordinates. So I have a half m z dot squared minus mgz, and then if I do a half beta squared over m minus beta squared over m, then I have minus beta x squared over 2m minus beta y squared over 2m. Right, I have one of them minus a half. I have a half of one minus one of them, so minus a half of them. So that's our Ruthian. So now you see an actual example of a Ruthian. Maybe the stuff I said earlier makes more sense. Like the stuff about what indices the sums are over. So let's look at our Ruthian. Our Ruthian has only one coordinate in it, and that's z. It's the one coordinate from the Lagrangian that was not cyclic. So for z, we expect that we're going to recover the Euler-Lagrange equation. For x and y, they are cyclic, and our goal was to arrive at a description that doesn't have any more cyclic coordinates in them. And so indeed, this Ruthian is two terms that depend on z minus two terms that are constants. Right? Those beta x and beta y and m are all constants. So our Ruthian truly does not depend on the cyclic coordinates. That doesn't mean that we don't want to know how the cyclic coordinates evolve with time. So we better be able to figure out what the equations of motion are for x and y. But we do have a description that doesn't involve them, which was the goal. So now we do the last step, which is to write out the equations of motion separately for the cyclic coordinates and the non-cyclic coordinates. That's by applying these equations A and B. For the cyclic coordinates, we apply B, and for the non-cyclic coordinates, we apply A. So the equations of motion let's start with the non-cyclic coordinates. So there's only one, right? Z. So the equation of motion needs to be the same as the Euler-Lagrange equation, but with r's instead of l's. So we have di r by di z dot minus di r by di z equals to 0. So let me look at r. So di r by di z dot, that's easy, right? There's only one term with z dot in it, so I differentiate with respect to that. The z dot squared, the 2 comes down and cancels the half, and so we're left with mz dot. So I have d by dt of mz dot minus di r by di z. How does r depend on z? It's minus mgz, so di r by di z is minus mg. And there's a minus sign in front of that here, so then it's plus mg. Right, there's a minus sign in front of the di r by di z. So di r by di z was negative, and then times the minus sign makes it positive. And that's equal to 0. And then you're not so surprised that the m's cancel, right? And then d by dt of z dot is just z double dot, and so we have z double dot equals minus g. That's good. That's what we hoped for. It's a particle in a gravitational field, so we expect it's going to accelerate downwards. So in this case, it's easy to solve, right? You could easily solve the second order differential equation of z double dot equals a constant, right? That just gives you z equals z naught plus v naught t plus or minus half gt squared. But it could be more complicated, right? You could have, if it was a more complicated system, this would have given a more complicated second order differential equation to solve. Now let's do the equations of motion for the cyclic coordinates. So let's start with x. So how do we do it? Well, we have to apply equation B. Equation B tells us that our cyclic coordinate dot is equal to minus di r by the corresponding beta. So x dot is equal to minus di r by di beta x. So dx by dt, just to write it out as a differential equation, that's what x dot is, right? X dot is dx by dt. So I need minus di r by di beta x. Okay, so I'm going to look at r. So I only have one term with beta x in it. And so when I take the derivative with respect to beta x, it's beta x squared, so the 2 comes out and cancels the 2. And note that I have a minus sign out here, so that's going to cancel the minus sign in front of di r by di beta x, right? So if I take that derivative and take the negative, I get beta x over m. And then similarly for y looks exactly the same as x. So the differential equation for y is going to be dy by dt equals beta y over m. And those are trivial to solve, right? That means x of t is equal to some integration constant x naught plus beta x over m times t. And the same with y of t. Of course, that's exactly what you expect, right? Beta x over m, that's just the same as dx, because beta x is the value that the momentum in the x direction has, so that divided by m is the constant speed v. And that beta y over m is equal to vy for the same. Of course, the top equation is easy to solve as well. The one for z, right, z of t equals z naught plus z naught z times t minus a half gt squared. It just happens that that one's easy to solve because it shows a trivially easy problem. However, that may not be the case, and so this Ruthian method does actually simplify things. And the way it does it is by making you focus on solving the equations for the non-cyclic variables, the z's, because those are the hardest ones to solve, and typically for the cyclic coordinates, the equations of motion are easy to solve. And so you can see that it would be appealing if we can find a set of coordinates where all the coordinates are cyclic, because then they're all trivially solved. Because these differential equations you get for the cyclic coordinates are always first order in the coordinates equal to some constant typically. Not necessarily equal to a constant, but often. That's the end of the chapter. Now, I guess I'll leave it up to you what you want to do. I have two options. Option one is I can do another example of the Ruthian. So it's carrying out this procedure again, but with something a little bit more complicated. And that would probably take the rest of the lecture. Or I can just be available to help answer any questions you may have with respect to assignment 4 or the material in general for the midterm. But if that's the option that you choose, then I'm just going to sit here quietly, and if you have a question, I'm happy to answer. So would you prefer that I do an example or another Ruthian example, or that I'm just available to answer questions? So the Ruthian will not be on the midterm. So that means you don't want to see another example of it. But it could be on the final. Well, it could be on the final. So there's a way to vote here. Let me figure out what's the best way to vote. So you can vote yes if you want to do another example of the Ruthian. Vote yes. Otherwise, vote no. You can vote by the little check mark thing there. I voted yes. There's a little check mark thing above your name, above the list of the names. So far, we have a 1 yes from me to do another example of the Ruthian, and nobody else is voting. If nobody votes, then I'll just not do an example. You're not the most engaging bunch, Amy. Well, mostly no's, huh? All right. Well, that's good. I can save that example to put on one of the exams. I don't have to come up with an exam question. Oh, yeah, sorry. That's just messy. That was to mean it was the z component of the initial speed. That was a very tiny z. Okay, so it's clear that we're not doing any, not doing another example on the Ruthian, so I'll just stay available until 10 minutes to the hour. Answer any questions that you have. So I encourage you to have a look at the assignment 4. And I'll stop the recording.